All right, guys. Today we're going to be doing some more work with independent and dependent variables. But this is going to be a little different because we're going to have some data that is non-linear. All right. So let's take a look at exercise one here. It says Old Faithful is a geyser in Yellowstone National Park. The following table offers some rough estimates of the length of an eruption of one of these geysers, or Old Faithful, I should say, and the amount of water in that eruption. Okay, so if the eruption of Old Faithful lasts for 1.5 minutes, then the amount of water is right around 3,700 gallons of water that comes out, and et cetera, down the line here. So it says Chang wants to predict the amount of water in an eruption based on the length of the eruption. What should he use as his dependent variable? Okay, so this goes back to something we did in the previous video as to which one of these drives the other. Okay, and I think this one is pretty apparent here. You can tell that the length of the eruption would cause more water to be thrown out of this geyser. All right. So I'm going to say that the length of the eruption is going to be the independent variable. So I'm just going to label this one independent. Okay. And they're asking me which one is the dependent variable. Well, the amount of water depends on how long of an eruption that you have out of the geyser. All right, so I'm going to say the dependent variable is the amount of water. All right, so then they say which of the following two scatter plots should Chang use? And you see that basically what they've done with these two is they've put the length of the eruption on this one is on the y-axis, and the amount of water is on the x-axis. And on the one on the right here, they basically switch those around. All right. So since the length of eruption is going to be the independent variable and the amount of water is going to be the dependent, then we would want to use this graph right here. Okay. So there are a couple other questions that go along with this. Let me get rid of all of this and let's just reduce it down to the one we want to use. This is the graph that was on the right here. Notice that the length is down in the on the x-axis and the amount of water is on the y-axis. And here's the table. It says suppose that Chang believes that the variables believes the variables to be linearly related. All right. It says use the first and last data points. So that would be this one. All right, right here, and this one right here, to create a linear prediction model. Okay, and what they're basically saying is you could draw a line of best fit here. All right, but when they say make a linear prediction model, they're saying come up with the equation. All right, and as soon as we see that word linear, then we know that our model should follow y equals mx plus b. All right, so we've done this before. We've used y equals mx plus b before to come up with an equation. So let's try and do that. All right. First thing we're going to need is the slope. All right. So let's try to go to our slope equation. All right. y2 minus y1 over x2 minus x1. And let's plug in some values here. I'm going to plug in, let's take this one right here, and let's take this one right here. It doesn't matter which ones. All right. Oh, actually, they told me to use the first and last. Sorry about that. All right. Let's take the first and the last. All right. So that means the y values are 8,400 and 3,700. Okay. And the x values are going to be 4.5 and, 1.5, not 3.5. Okay, and then if I just do the math here, 8,400 minus 3,700 is going to give me 4,700. And if I subtract the denominator here, I'm going to get 3. All right, and then I'm going to make sure with my calculator, I'm going to bring that up here, and I'm going to do the division here, 4,700. And I'm going to divide by 3, and I'm going to see if that comes out even, which it does not. So I'm just going to leave it as that fraction right there. Okay, 4,700 over 3. So far we have y equals 4,700 over 3 x plus b. All right. Now, what's left? I have to figure out my y-intercept. And in order to figure out my y-intercept, we've done this before. All right. You take the equation, what you have so far, and you pick one of these points up here. All right. Let's choose this point. I'm going to use that point right there. So I'm going to plug in a 4,100 for y, and I'm going to plug in a 2 for x, and then I'm just going to solve for b. All right, so I'm going to bring up my calculator again so I can do that. I'm going to take 4,700 times 2 equals that, and then I'm going to divide that by 3. And again, that doesn't come out very even. All right, so I'm going to get 4,100 equals 3133, and I'm just going to go to the 10th here because that is not going to stop. That's a repeating decimal there. All right, and then I'm going to take away this on both the sides. Should be a decimal right there. Okay, and I'm going to get a value for b. All right, now my calculator up here, 4,100 minus 3133.3, and I'm going to get 966.7. All right, so 966.7. So that means I can go back to my equation right here, and this is going to be my equation for this model, plus 966.7. All right, so when they say build a prediction model, they're just really saying build the equation that would describe this if it is linear. Okay, of course, this section is on nonlinear models. You can see if you really connected the points here, it wouldn't make a straight line. All right. Okay, so we're going to use that and try to answer. I'm going to write that down here off the screen so I don't forget it. I'm going to use that to answer one of these others. All right, his friend of Chang's told him that Old Faithful produces about 3,000 gallons of water for every minute that it erupts. Does the linear model that you created support that? Okay, now if you remember, the equation, you probably have it right in front of you, the equation that we came up with looked like this. And the friend is saying 3,000 gallons of water for every minute. Okay? Now, what we could do, there's a couple ways we could do this. We could plug 3,000 in for y and solve for x. That would be one way. Or we can just look at the rate. All right? It's saying gallons of water for every minute. That is your rate. All right? Which we've always said is the same thing as your slope. So I could just look at this part right here, and I could say, does my slope, does that really equate to 3,000 gallons per minute? Okay, and I could do it with a proportion, or I can just divide these two and see what that comes out to be per minute. I think we already did this earlier, but I'm going to do it again. That actually would come out to 1566.7 per 1 minute. All right. So are these two? Is his friend correct? All right. And no, this is very far off. Right. Very far off from the 3,000 gallons per minute that his friend thinks it is. All right, so my answer to this would be no, he's not correct. Okay, and then the other question that goes along with this, using the linear model, does it make sense to interpret the y-intercept in the context of this problem? All right, and think about what the y-intercept means. The y-intercept is when x is 0, right? So I'd be plugging in a 0 here. And that would be like at 0 time, right? With 0 amount of time that went by, you've got 966.7 gallons of water being thrown out of this geyser. And that wouldn't make sense, right? If it erupted for 0 amount of time, right? Remember, x is time. Why would any water have come out? Well, no water would have come out. So no, the y-intercept in this case does not make any sense in this problem. All right? So that is exercise 1. Let me clear everything off, and we'll go on to exercise 2. Okay, guys, here is number 2, and we've got another table. And this shows the year of the Olympics along the top here. And it shows the times for the gold, silver. Let me get on the right layer here. The gold, the silver, the bronze, and the mean, which means the average. They've averaged these times, okay, of each of these years. So they're talking about the 100-meter, the 100-meter race. And if you wanted to describe how mean time changes over the year, they say which variable would you use as the independent variable, and which one would you use as a dependent variable? All right. So if we're looking at just the year and the mean time as far as the variables go, which one is totally independent does not matter in relation to the other one. Well, the years, they do not matter as to what the times were, but the times definitely matter, because usually as the Olympics games go on, they get more recent, the times improve. All right, because athletes get better, they have better training methods, and they always try to beat those old records, So years are going to go on regardless. All right, so that is going to be my independent variable. I'm going to label this one, I'm going to just put IND for the dependent variable, or the independent variable, sorry. And the dependent variable, I'm going to put DEP, that's going to be the dependent variable. All right, so what they want us to do, if I switch over to this one right here, they want me to draw a scatter plot to determine if the relationship between mean time and the year appears to be linear. Okay, now what I went ahead and did, and I sketched myself a little graph. What I'd like you to do is just pause the video and sketch this graph. And I'm going to go ahead and label, we said the independent is going to be down here. I didn't put I just put 76. Okay, you can put a little apostrophe there. That's how we abbreviate years. 82 or 88, 92, 96, etc. So you can put a little apostrophe there. So I just put the years along the bottom. And then over here is going to be the mean time. And I looked at the mean times, and I didn't have to go any lower than 9.5. And I didn't have to go any higher than 10.3. So what I did is I just put some little hash marks here, and I made each one of these hash marks be 0.1. All right, so we got 9.5, 9.7, 9.9. I went every other hash mark so it wasn't all squeezed in. So just pause it and just copy that down. And then go ahead and graph. We're graphing the years again and the mean time. I'm going to go ahead and do this. I don't want you don't have to watch me graph all these, but go ahead and pause the video and just graph them, and I'll do the same with mine. Okay, so you can see that I sketched the scatter plot here, and you can see why we're saying this is not linear, because if I just connected these points, that definitely wouldn't be a straight linear line. But we can create a best fit line that could be linear. We could draw this in, and we could try to hit as many points as possible. Oh, that's just a bad line right there. Let's do that a little better. Okay, we could try to hit as many points as possible and then keep... I'm trying my best, guys. All right, let's see. I could use a ruler, that might be better, but this is very hard to use, all right, with I'm going to try to sketch it a little bit at a time. What if I did something like this? All right, that might be a little better. Okay, see, I hit a lot of those points, and I've got a couple, 2 of them up here and 3 of them down here, and I hit those other points. So, if we did a best fit line, that would be a linear line, and the trend seems to be as the years got bigger, right? As we got more recent, the times tended to go down. All right. If you didn't pick up on this, I reversed. I started 1976. Right. I wanted to go chronologically, so I started down here and went that way. All right. So there's your scatter plot. I believe they asked us to do something else with this as well. It says using the years. Can I turn that off? Yeah, using the years 1992 and 2004, draw a linear line of best fit, which we just did. Okay, and then find the equation of that line. Okay, so we're going to say find the equation of that line, which again, y equals mx plus b. I need to find my slope first, right? So my slope, I'm going to be using 92, which is right here, and 2004, which is right here. So my slope, my y values are the time, so that's going to be 10.01 minus 9.86, okay? And I'm going to put it over the years. That's going to be 1992 minus 2004. Okay, and then I'm going to bring my calculator up to make sure I multiply these right. All right, so we're going to have, or subtract, I should say, 10.01, and I'm going to subtract 9.86, and I get 0.15. Okay, so 0.15. And 1992 minus 2004, should be able to do that. I'm just going to make sure here. Okay, negative 12. All right, which makes sense because remember our graph, right? Our graph went down to the right, so we should get a negative number. I'm going to see what kind of number this comes out to be. Negative, divided by 12 and make that negative. There we go. Yeah, I can do that. 0.0125. Okay, 0.0125. So there's my slope. Okay, so far, this is what my equation looks like. And if I want to find the Y-intercept, which really in this case it's not going to make a whole lot of sense for the Y-intercept in this problem, but we can find the Y-intercept by picking one of the points. Okay, let's pick one of the points. Let's just take 1992. All right, so we'll use this one. We'll use 1992 for x, and y is going to be 10.01. Okay, and so I need to take this number times 1992, and that's going to be negative 24.9. Okay, so I have negative 24.9. All right, and then I'm just going to add 24.9 to both sides. And what am I going to get for b? I'm going to get 34.91. So that means my equation is going to look like this. And what did I just get? Plus 34.91. Okay, which again, in this problem, I don't think the y-intercept would really mean anything. All right, other than that would be your predicted time if you went back to year 0. You know, what does that really mean? Doesn't really mean much in this problem. Okay, but same idea as the previous example there. So it works. It works. Okay, so hopefully you could follow that. Thanks for watching. Have a good night, and we'll see you in the morning.